Hey chemistry guys, we are going to be doing another video right now on Friday. It's about 12:27. Hopefully I'll get this up in the next couple minutes. I wanted to go over some of the questions I had left you guys with over the week, just to give you a step-by-step procedure to answer them. At some point you are going to have to answer these questions in a test or quiz-like environment, and so you really should know how to do this. Hopefully you're looking over the keys. As a reminder, the keys are just in the normal assignments folders in semester 2 for thermochemistry. All of the questions that I'm using for our online learning come from those homeworks as well. So I want to go over a couple of them today. This one in particular, I love this question. This one is great because it's about cooking, and cooking is fun. We want to figure out in this question the specific heat of chicken. And the question says, in a frying pan, 300 milliliters of oil, which has a density of 0.9 grams per milliliter, are raised from 22 degrees Celsius to 190.6 degrees Celsius. A 500-gram chicken breast at 22 degrees Celsius is cooked in the oil until it reaches 75 degrees Celsius. The specific heat of oil is 1.79 joules per gram Celsius. And what is the specific heat of chicken? So in this question, we are asked basically to find that constant called the specific heat, which tells us how much energy it takes in joules to raise 1 gram of a substance by 1 degree Celsius. That's the specific heat. Let me draw a picture of what this is essentially looking like. So we've got a pan. An awesome drawing, I'm sure, to many of you who are really good drawer people, artists, whatever that's called. I don't know. It's a pan. Okay, and in that pan we've got some olive oil. It's yellow. Olive oil is yellow. And in that pan we've got a piece of chicken. Chicken's kind of pink. We'll put it there. Okay. So we're doing a standard pan searing of chicken and some olive oil. And that olive oil, its temperature change is it finishes off at 190.6, and it originally was at 22 degrees Celsius. So it heats up, and the chicken here, its change in temperature is finishing at 75 degrees Celsius and started at 22 degrees Celsius. So the oil is being used to heat up or cook the chicken. And we want to figure out what the specific heat is. At the end of the day, this is a law of conservation of energy question, where the amount of energy that the oil gives to the chicken is exactly the amount of energy that the chicken receives. There's no loss of heat in that transfer. So the Q of the oil is the amount of energy that the chicken receives as well. Now, when we do this problem, we don't really have to worry about whether it's exothermic or endothermic, because there's really the amount of heat changing is kind of weird in this one, because we've got the fire here keeping the oil at the same temperature at the end of the day. So the oil isn't changing in temperature, it's not dropping down in temperature, it's staying at 190.6. I think that's kind of the tricky part about this question. But at the end of the day, the oil is being heated up to 190.6. It's being kept there, and then that cooks the chicken up to 75 degrees Celsius. And then the oil is the transfer medium for that heat. But at the end of the day, the law of conservation of energy holds true. The amount of energy that the oil gives to the chicken is the amount of energy that the chicken receives. To be really specific, for the oil, this is an exothermic process. It's transferring its heat to the chicken while simultaneously still being heated by the fire down here on the burner. And the chicken is gaining heat, so that's endothermic. But for this problem, I'm not going to worry about negatives because it actually messes up the calculation. That's kind of the tricky part about this one. If this were a situation where we're not continuously being heated by a burner down below, if you just had like a hot thing and put that in water and cooled it down, that is where you would have to worry about negatives. But in this case, it's kind of tricky. You don't worry about the negative. But anyway, at the end of the day, we can break this down into mcdeltaT for the oil equals mcdeltaT for the chicken. All right, let's just go ahead and put our numbers in here. So The mass of the oil, we don't know directly. We are told the volume of the oil, and we're told the density. So we can figure out the mass by doing our density equation. Remember, density is the mass of a substance divided by its volume. So the density is 0.9 grams per mil. I don't know the mass. The volume is 300 mils. Okay, so 0.9 times 300, that equals 270 grams. So I've got 270 grams of oil. 270 grams times the specific heat of oil, which I am told is 1.79. And the change in the temperature of the oil is, like we have here, 190.6 to 22. So its final temperature is 190.6 minus 22. I'm going to kind of run out of room here, so I'm going to rewrite that. So 270 grams, 270 times 1.79 joules per gram Celsius times 190.6 minus 22. And that equals the mcΔT for the chicken. The chicken, I was told, is 500 grams. I don't know the specific heat of the chicken, but I know the chicken heated up to 75 and started at 22. All right, so now just do our number crunch here. So on the left side, we've got 270 times 1.79 times 190.6. Whoops, 190.6 minus 22. Okay, so 81484. We'll just do the 5 sig figs. 81484 joules equals, and on the left side, 75 minus 22 times 500, oops, 26500. 26500 times C. Okay, and then just divide on both sides. So C comes out to be 81484 divided by 26500, and our answer is 3.07. So the specific heat of chicken, 3.07 joules per gram Celsius. And you might remember that I told you specific heats for most substances are really low, like metals and stuff like that. Chicken obviously isn't a metal, but chicken at the end of the day is, well, it's chicken. It's the animal. And cells. What are cells mostly made of? They're made of water. So this specific heat is pretty dang close to the specific heat of water, which you'll remember is 4.18 joules per gram Celsius, right there. So something to just kind of keep in mind. Specific heats are usually really small numbers. Most substances aren't really good at taking in heat. Some are, like insulators, like water is one of them. But cells are pretty good at taking in heat. And that's a good thing for us too. Specific heat of a human muscle cells probably pretty close to a chicken's. All right, let's look at some other problems here. All right, this one has to do with enthalpy. It asks, what mass of iron must react to produce 3,600 kilojoules according to the reaction right here? So this reaction, iron reacting with oxygen making Fe3O4. And the enthalpy of the reaction is minus 1120 kilojoules per mole reaction. I didn't actually do a problem in this direction with you over the lecture video last time. I wanted to see if people could figure this out on their own. It's really just a stoichiometry problem. We're just doing it in reverse. Instead of taking with mass or moles, we are going to be taking the energy and converting to moles of reaction, then moles of substance, and then grams. So let's take that and do this one. So if we wanted to make 3,600 kilojoules of energy, okay. Now to keep things kind of simple here, this is an exothermic reaction. So if I wanted to generate 3,600 kilojoules of energy, that would be released because the enthalpy for this reaction is exothermic. So I'm going to put a negative there. So 3,600 kilojoules. Okay, and then I'm going to multiply by the enthalpy of the reaction to get moles of reaction as the as the unit I want, and then convert from moles of reaction to moles of iron. So for every 1 mole of this reaction happening, remember that's like 1 cycle of this reaction, negative 1120 kilojoules of energy are released. Okay, that's going to get rid of our negative really fast. We're not going to have a negative number now. And then for every 1 mole of this reaction that happens, 3 moles of iron are used. If you can hear that in the back, my cat is deciding to do something crazy. I'm not sure what she's doing. And then to convert to grams, we're going to just go from moles of iron to molar mass, 55.85 grams. Okay, so that's how we would do this one. Let me just do the number crunch. It's going to get rid of the negatives, so I'm not going to put the negatives in my calculator. 3600 divided by 1120. Okay, and then times 3, and then times 55.85. Times, so 9.642857 times 55.85. So my answer is about 538.5, so we'll do 539. My cat is making a very annoying noise. I'm going to go figure out what that is. I'll be right back. Okay, we're back after the cat, I think, wanted food. Anyway, here we go. So the answer to this question was 539 grams of iron. We need, in order to produce that much energy in kilojoules, we would need to use 539 grams of iron. Okay. Last problem I want to go over is actually the last problem from Thursday's assignment. This has to do with enthalpy of reaction, and then actually finding it given some information about some salt dissolving in water. So it says, excuse me, in an experiment, 7.46 grams of potassium chloride are dissolved in 100 milliliters of water at 24 degrees Celsius, 24.1 degrees Celsius. The solution cools to 20 degrees Celsius. What is the enthalpy of solution in kilojoules per mole? So remember, the enthalpy of a solution at the end of the day is going to be equal to the amount of energy that the reaction produces, whether that's endothermic or exothermic, divided by the number of moles of reactant that happened or were used in that process. The reaction that we're looking at is this one. So sodium chloride, the salt, is being deposited into water and it ionizes. Okay. We want to figure out when this happens, when salt dissolves in water, how much energy is released per mole of that salt being dissolved in the water. They tell us that the change in the temperature is, it starts at 24.1 and then it goes down to 20. So its final temperature is 20, subtract 24.1. So our change in temperature is minus 4.1 degrees Celsius. That's an important number to keep in mind there. We're going to use it because this is just mcdeltaT over number of moles. Okay? Now, one thing also to keep in mind here is I can't directly calculate mcdeltaT for these ions. I can't do that. Why? Because I don't know the specific heat of potassium ions, chloride ions. It doesn't really make sense. But what I do know is that when the potassium chloride went into water, okay, when I did that, I know that the temperature went down. And I need to remember, this is a big deal here. I need to remember that this is true always. The amount of energy that occurs with this reaction, with these ions forming, with the salt dissolving, that is equal to the amount of energy that the water receives or gains. In this case, this is an endothermic reaction. How do I know it's an endothermic reaction? I know that because the temperature of the solution went down. It went down. So that means that when the salt dissolves, energy in the water molecules, that's going to be given to the potassium and the chloride ions. And so in my hands, this will feel cold. So the reaction, the dissolving process, that's endothermic. And the water giving heat to the ions is exothermic. Now I can calculate this. I can calculate that because I know the specific heat of water. And if I figure out that value here, then I can transfer it over here and then use that in this equation up here. So let's go ahead and do that. So the Q, the heat of the water, is going to equal the mass of the water. They tell us that the mass or the volume is 100 milliliters, so the density of water is 1 gram per mil. So that means I've got 100 grams of water. And then I know the specific heat of water, 4.18 joules per gram Celsius. And then the change in the temperature of the water, I just calculated that. It's negative 4.1 degrees Celsius. So Q is going to be 100 times 4.18 times negative 4.1. So I get negative 17, we'll do 14 joules. Now that's for the water. For the reaction itself, it's going to be endothermic, so it's going to be positive 1714 joules. And I want to get that in kilojoules per mole for enthalpy, and that's going to be 1.714 kilojoules. I think I need to pause the video again. Okay, sorry about that. We had an issue with a spider and a toddler coming in at the same time, so that was fun. Anyway, we're right here. We figured out the amount of energy in the dissolving of the salt, and we found that the water would have given off 1,714 joules of energy, and we figured that out because the temperature for the water changed, so it gave its heat to someone else. It gave that heat to the potassium chloride, and it therefore lost heat, and therefore its temperature dropped. And therefore the process, the reaction, the dissolving of the salt would have gained that energy, 1,714 joules, and that is equivalent to 1.714 kilojoules. Why did I turn into kilojoules? Because enthalpy is always given in kilojoules per mole. So there are 1,000 joules to 1 kilojoule, so that gives me 1.714 kilojoules. And then I'm going to finish off by putting in the amount of moles in that deposited into the water here. So my enthalpy is going to be equal to, kind of a little extra room here. My enthalpy is going to be equal to 1.714 kilojoules divided by the number of moles of potassium chloride. I can do that over here. So we had 7.46 grams of KCl. I'm going to convert that to moles of KCl. Oh gosh, molar mass of KCl. Let's look that up. 74.55. 74.55. So 7.46 divided by 74.55, and that's going to give me 0.1. Okay, so we're going to divide that energy we calculated by how many moles of potassium chloride dissolved in water, and that's going to be 0.1 moles. Okay, so 1.714 divided by 0.1, that's going to be 17.14 kilojoules per mole. And there's our answer. That's the enthalpy of the reaction. Okay. Last question utilizes that number we just calculated. So our enthalpy is 17.14 kilojoules per mole. And the question is, what mass of KCl is necessary to transfer 3,000 kilojoules of energy? We just did something very much like this. So we're going to go from kilojoules to moles of KCl and then grams of KCl. So 3,000 kilojoules, that's how much energy we want to transfer in this problem. We're going to convert that to moles of reaction. So in 1 mole of the reaction, 17.14 kilojoules of energy are released. And then in 1 mole of the reaction, well, 1 time, how much KCl? Well, there's a 1 here. So 1 mole of KCl is dissolved. Okay? And then convert to grams. 1 mole of KCl is, what did we just calculate? 74.55 grams of KCl. All right, so there's our math. So 3,000 divided by 17.14 times 1, and then times 74.55. And so our answer is going to be a pretty big number there. 13,048. We'll do 13,050, just to round it nicely. So 13,050 grams of KCl is our answer. And there we go. All right, so these are the answers to some of the questions that were given over the past few days. Please let me know if you have any other questions. Some people are messaging me or putting questions up on the discussion board, whatever works for you. I'll get back to you as quickly as I can. As you can see, I have various things that happen throughout the day, so it keeps me busy plenty. But happy to help in any way. Let me know. Do expect some kind of real quiz next week when you look at next week's work, as we're all stuck inside having a lot of fun. Though it is nice and warm outside and sunny, so enjoy that over the weekend as well, guys. Have a great day. Bye.